Just a few quick comments before we open up for the entire, I guess, panel discussion. I'm not sure, it's either an example of great minds running in the same rut or groupthink, but largely much of this has been said. The one piece, one datum that I don't think has been said yet is we haven't yet noted one of the reasons for focusing on radio, and actually I think Paul or somebody already sort of referenced this obliquely, is radio and gamma rays are really the only two parts of the electromagnetic spectrum in which the galaxy is almost completely transparent. In terms of leakage, I show this because I've actually done a bit of work with this. This is what used to be NAV Spacer, the Naval Space Surveillance System. It's now the Air Force Space Surveillance System. But this is an excellent example of leakage. It's a transmitter. This particular one's in Texas. And you can imagine as the Earth rotates, this radar beam sweeps across the sky. This one happens to be at 217 megahertz, so it's below the frequency that we seem to be focusing on these days. But it is essentially like a megawatt transmitter, and that is detectable over interstellar distances. What I did want to, one of the things that I keep coming back to in this workshop is what I think is a perhaps artificial distinction between SETI and, quote, normal or traditional radio astronomy. If you look at 21st century astrophysics, what have we been able to do? Well, we've actually been able to detect, either from ground or space, almost the entire electromagnetic spectrum. Certainly in terms of, as Paul and some others have shown, if you look at the radio millimeter and submillimeter band as almost coming online, we're going to have exploited pretty much all of the ground-based radio RMS spectrum that's available. Polarization, well, it's either standard or it's so difficult nobody wants to bother with it, but it is easily accessible. Angular resolution, we can do extremely well in that. The areas where we're having problems are areas where the challenges are for, certainly I think, at least radio astronomy, and perhaps even ground-based optical, is mirroring time and field of view. We've done one of these very well. And we can, I'm trying to remember if it's actually been published from the Green Bank telescope, but certainly from the Arecibo telescope, there have been nanosecond time bursts that have been resolved from the Crab pulsar, which is, just from an astrophysical standpoint, remember a nanosecond fits inside this room. So the Crab pulsar is somehow generating within its magnetosphere these pulses that are from some area that could fit inside this room. And then field of view, I'm not sure if I have a picture, but I've certainly been involved in a project in which we were able to obtain essentially 2 pi steradians of the sky. And so the challenge, this isn't turning out very well, but the challenge, what this is a picture of the radio sky actually over Green Bank. So I believe that little, if you can see a white blob there, that's the old 300 foot. This is the radio sky as seen over Green Bank, and it's apparently in a very static, it's the traditional picture of a very static radio sky. But in fact, as we've been hearing, this is one of these rotating radio transients or RATs that's been referenced. Here's a single pulse, and here you can see the dispersion. What you're seeing here is actually flares from or pulses from a brown dwarf, which originally was a project a bunch of students at the VLA, a bunch of summer students at the VLA did, and the scientific staff sort of tolerated this wild idea, but we all know that brown dwarfs aren't going to emit in the radio, and lo and behold, they actually found some. And then Greg Hallinan, who's now a postdoc at NRAO, has been doing this. This is actually a source in which I was involved. A classic example to illustrate the serendipitous aspect. I had a colleague, this is part of the Galactic Center, and he became familiar enough with the Galactic Center that we had several epochs, essentially, of images of the Galactic Center. And he said, "What's that? That's not supposed to be there." It's like, oh, well, let's chop up the data and see if it's still, is it some kind of weird interference? And lo and behold, it actually was a pulsing signal. Came back every 77 minutes. It came up for like 10 and went down. I think, depending upon how you count the number of observations, the number of models is either equal to or it's either greater than or comparable to the number of actual observations to explain this thing. And so the point of this, where I'm headed with this is we perhaps should not, I have been struck by the extent to which SETI has often been distinguished from sort of traditional radio astronomy, and yet we seem to be moving in this direction of trying to understand the universe. And in fact, this is not just in the radio. Here are some of these next generation radio projects, but One of the high priority items recommended in the United States is an optical sky survey telescope looking at the time domain. And you can even take it to Chris Rose's suggestion, if you want to find matter packets, well, the question has come up, how well do we actually understand our own solar system? We should be exploring our own solar system. Now, why are we doing that? Is it because the asteroid belt somehow contains a record of the evolution of the solar system? Or is it because we might find something, some packet of matter and densely encoded matter? It's not an either or, and I think that's the thing that I've been taking away from this workshop, is that we really should be thinking of this as both time domain and sky. Let's survey the sky, let's understand the universe in which we live, and if we happen to find life, great, but even if we don't, we're still in a much better position. With that, with whatever remaining time we have, I would open it up for general discussion of everything from, I guess I would say, the strong force modulated messages to weak force to the photonic or electromagnetic. Okay. Jay.
I hate to even bring this up, but it's sort of unfinished business in my mind. In the process of organizing this workshop, I've come across little packets of information about things I know nothing about. And I somehow associate this one with you, Chris, and that is the idea that there is something in our genetic code which shouldn't be there, an artifact, in fact.
That's a good question and a bad question, but I'll handle it to the best of my ability. That was one thing, and again, Paul has been a patron saint in this. He kind of took me under his wing, Paul Harris. And you talk to the molecular biologists, and life is all one show. And that's a quote. Life is all, it's all one show. The communication theorist in me wants to know how you would detect an incursion, if there were such a thing. So, finding something in the genetic code, that's a little outre. I take it from the standpoint of communications problem. If I were trying to put something in a genetic code, what would I do and how could I detect it? So I'm not going to, I guess I am an ET agnostic. As I think about most people, a lot of people are here. I want to do the science and see what the detection possibilities are. Does that answer your question?
Yeah. I'll just mention there was actually an obscure publication 35 years ago by a Japanese group, you've seen it, claiming that they had found the signal in the DNA sequence.
In microphage, yeah, I was just trying to look that up.
Phi-X174 was the bacteria.
Now, is this, if you're just looking it up, is that an example of improving our intelligence? Or becoming too...
I didn't find
You don't have to answer
it.
it.
Smarter.
Jeff.
I just have a comment about neutrino searches and neutrino astronomy in general. The problem with neutrinos is that we're not focusing them, so that we're not looking at a particular point on the sky. But of course, neutrinos can be focused. Like all other forms of radiation, you can focus them with a gravitational lens. And the interesting thing about the gravitational lens is that with the gravitational lens at 550 AU, the reason it's at 550 AU is that we're looking at the limb of the sun. But the core of the sun is much more dense. So as a neutrino focus, the focal length of the gravitational lens of the sun is much, much closer because they're focused by the core of the sun, not by the outer part. So actually, if we're really serious...
Do you know where it is?
It could be calculated pretty quickly.
Okay.
Any astrophysicists around here? No, SETI people, no astrophysicists. So, if we're talking actually about neutrino astronomy and neutrino SETI searches, you really want to look, using a lens, not just using isotropic neutrinos.
Are you calculating? No. I'm just writing this down for this. This is a good idea. Tom?
It seems to me the one thing that's consistently missing in many discussions at this meeting, which should be included, is the possibility that a society moves into space. We hear discussions about people willing to discuss societies or life forms eking their existence out around a young dwarf. You know, if biology will have its way around a planet around a young dwarf, biology will have its way pushing people on an Earth-like planet orbiting a G-star into space. They can, and you know, it would, for people who like to think about interstellar colonization, it's vastly more likely that interstellar colonization would start from a society that lived predominantly in space than from a planet. I agree with everybody who's, you know, nobody's going to colonize from a planet. So it would change that, but it also, even if they can't get out of their stellar system, they would probably have a totally different philosophy on sending out beacons. They probably could give a hoot about communicating through atmospheres, so that would push towards shorter wavelengths. And they would have probably different forms of leakage radiation. And I think, I don't know, this community seems to ignore this, and every time I say it, I get laughed at. But you know, we should think about it a little more.
So what should we be looking for that's different? You mentioned higher frequencies, and we're trying to get there.
Yeah.
IRS, SRS, stars.
Yeah, well, there are people talking about, you know, Dyson spheres, but I think a society, as I would imagine, it probably doesn't collect anywhere near its own solar radiation, so it would be a small amount of IRF says.
You know, at Fermilab, Dick Kerrigan is looking in old survey data for candidates for Dyson spheres,
Yeah,
or looking to rule them out, I guess.
There are a whole bunch of those. We did a search like that too.
It strikes me, going back to the theme you're proposing, I agree with you totally that everybody who studies astronomy is doing SETI. And what I think this, because every time we're collecting data, it's data that somebody can go back and look at with the SETI filter, with the SETI eye. So I think the important thing for the SETI community to tell the rest of us astronomers is, number one, what to keep an eye out for in the data we're collecting, and two, what to do with it if we find it. In particular, I get frustrated sometimes hearing people say, well, we have to be willing to think outside the box. Astronomy works because of filters. Yeah, if you use the wrong filter, you're going to miss the signal. But if you don't use a filter at all, you're also going to lose the signal.
Yeah, I agree. I think you have to put filters to do meaningful science. But I think if you, after you apply the filters, you get some weird glitch. If you have some time, don't just say, oh, that's a bad data point. You know, try to pursue that.
And so my point is, as a non-SETI person, you know, if you could give me a little card I carry in my back pocket, this is the kind of thing that an interesting glitch would look like, that would help.
But if Jill Selma wrote it.
Yeah.
Actually, I think that's the wrong way around. I mean, I think it is, you should look at the data and see what you see. And if it doesn't fit in with your preconceived notions of what you should be getting, start exploring it for interesting astrophysics. And if that runs into a brick wall, then think about it as a potential astroengineering artifact. I think our theorists have shown us that when you come up with something new observationally, it doesn't usually take them very long to say, aha, it's a this.
I could have predicted that only I thought. Yeah.
They're very flexible.
Right, so if they don't come up with it quickly, then maybe astroengineering is a good next step to think about.
Tom?
Just an advertisement for tomorrow morning for any of you who have flexible travel plans. Try to be here for sure for tomorrow morning's strategy discussion, because it's going to focus, the panel is going to focus on what does the next 50 years of SETI look like. And we should be bearing down on the sustainability of SETI or not, and what should it look like. And try to be here. I think it's going to be a very important discussion.
Yeah.
One.
Go ahead.
Well, go ahead.
Actually, I have a question.
Yeah.
Yeah.
For Dan.
Oh.
Right, is that legitimate? Can you ask from panel to panel?
Is that bad?
No, go for it, go for it. But make it quick.
No, so this is complete naive. So you're basically, you have all this data and your big computers and you can do data mining. And this is kind of the Jill too. Can you do something like a Graham-Schmidt? I mean, so it was stimulated by your comment that you're looking at it in terms of filters, but can you do kind of a Graham-Schmidt sort of thing where you just
We've been playing
contract off
around with
principal
these,
components?
Principal component analysis is exactly what we've been playing around with. It's a hard thing to do, and we just fooling around with those algorithms. But that, just for the people who don't know what principal component analysis, this is just finding some non-Gaussian signal in your data. It just looks for the strongest thing that's not non-Gaussian. It tries to fit orthogonal basis sets to your data independent. So the Fourier transform tries to fit sine waves, which are an orthogonal basis. But there are an infinite number of orthogonal bases. And the principal component analysis does exactly that. And I think it's a hard computational problem, and there's interference, and people play around with that a little bit. But I think that's an excellent suggestion, and you're not the first one that suggested it. Great minds think alike.
So, Chris, every Friday we record about 8 hours worth of raw data from the beamformer on the ATA, put it on the web, put it on the Amazon Web Services. SETI Quest will let you download that and analyze it any way you want. We're really trying to look at different visualizations and different algorithms for different kinds of signals.
Yeah, and correlated against known physics. That was really the trigger for this.